Welcome to the Explainer. Have you ever tried to push two identical magnets together and felt that invisible cushion of resistance just bouncing them apart? We physically experience that push in our hands, but there's actually an entire invisible landscape of pushing and pulling happening all around us at the atomic level all the time. So today, we're going to make that invisible landscape visible. We're going to map out the topography of electrostatic potential and see exactly how energy is stored in the very fabric of an electric field.
Okay, let's dive right into this with a pretty simple question. What actually happens when you push a charge against an electric field? Think of this as the start of our hero's journey. We've got this tiny test charge, and we're going to force it to go exactly where it absolutely does not want to go. Now, to understand what happens to all the physical effort we put into pushing that charge, we actually need to look at something a lot more familiar to us.
It turns out the electrostatic world behaves just like gravity. Think about lifting a really heavy box against the pull of gravity. You're doing work, right? And that work doesn't just vanish, it's stored in the box as gravitational potential energy. If you drop the box, boom, that energy is released as it falls. Well, the Coulomb force between two charges is also a conservative force. So, just like lifting a mass stores energy, pushing a charge against a repulsive electric force does the exact same thing. You are doing work against the field, and that work gets stored up as electrostatic potential energy.
So here's our roadmap for the Explainer. We're going to explore the invisible landscape, define electrostatic potential, look at point charges and dipoles, map out equipotential surfaces, and finally, scale all the way up to calculate a system's total energy.
All right, let's jump into part 1, the invisible landscape.
Let's introduce our protagonist. Imagine a tiny positive test charge. We'll call it little q, and we're moving it from point R to point P. It's being pushed toward a much larger positive charge, capital Q. Since they're both positive, they naturally repel each other. Now here's the trick. To move Q without it speeding up or accelerating, we have to apply an external force that is exactly equal and opposite to that repulsive electric force. We're bringing it in infinitesimally slowly. All the physical effort we exert, literally the work we do against that repulsion, gets fully stored in little q as potential energy. If we were to just let go, the electric force would instantly take over, throwing q away and converting all that stored potential energy right back into kinetic energy.
Moving right along to part 2, defining electrostatic potential.
Now, to really get this, we've got to tackle the biggest sticking point for anyone learning this physics. We absolutely have to separate the concept of energy from the concept of potential. They sound super similar, but they're critically different. Electrostatic potential energy difference is the total work required to move a charge from one point to another. The absolute value of the potential energy doesn't really matter physically. It's the difference in work done between the 2 points that actually means something. We usually just choose infinity as a convenient 0 point. And here's a beautiful fact about this. Because the electric field is conservative, this work depends only on your starting and ending points. It is completely independent of the path you take. You could take a straight line or take a detour around Jupiter. The energy difference is exactly the same.
But here's where we make a crucial shift when we define electrostatic potential, which we represent with V. The concept we just talked about was the total work for any random charge Q. Potential V, however, is the work done per unit of positive charge. By taking the total work and dividing it by the amount of charge Q, we get a value that's a characteristic of the electric field itself. It's completely independent of whatever tiny test charge we use to measure it. So rule of thumb, energy is the total work, potential is the work per unit of charge.
That brings us to part 3, point charges and dipoles.
And this brilliantly illustrates how different arrangements of charge create totally differently shaped invisible landscapes. If you look at a single isolated point charge, the electrostatic potential drops off somewhat gradually as you get further away. It's proportional to 1 over the distance, or 1 over r. But the electric field itself, it falls off much steeper, proportional to 1 over r squared. This basically shows us that as you walk away from a point charge, the actual force you feel drops off way faster than the accumulated work you did to get to that spot.
But what happens if our source isn't just a single isolated charge? Let's contrast a point charge with an electric dipole, which is just a positive and a negative charge sitting a tiny distance apart from each other. While a point charge's potential only depends on your distance from it and drops off relatively slowly, a dipole behaves entirely differently. Because those positive and negative charges sort of cancel each other out when you look at them from a distance, the dipole's potential falls off much faster, at a rate of 1 over r squared. And honestly, the coolest part is that for a dipole, your potential depends on the exact angle you approach it from.
If you approach right along the equator exactly between the two charges, the potential is actually zero.
Okay, let's jump to part 4, mapping equipotential surfaces.
Since all these potentials are completely invisible to us, physicists map them out kind of like how cartographers draw contour lines on a topographic map. An equipotential surface is exactly what it sounds like, a surface with a constant value of potential at every single point. Because the potential is the same everywhere on it, the potential difference between any 2 points is exactly 0, which means it takes absolutely 0 work to move a test charge along the surface. Imagine you're walking around the side of a massive steep mountain. If you hike straight up to the peak, it takes a ton of work. But if you walk along a perfectly flat, level trail that just wraps around the mountain at the same elevation, it takes 0 extra effort against gravity. That flat trail? That's an equipotential path.
So for a single point charge, these zero-work paths form perfect, concentric, spherical shells radiating around the charge. Now, if you look at the electric field lines pointing straight out, notice how they always intersect those spherical surfaces at a perfect 90-degree angle. This is actually a really strict fundamental rule. Electric field lines are always perfectly perpendicular to equipotential surfaces. Think about it. If they weren't, the field would have some sort of sideways pull along the surface, which means you'd have to fight the field and actually do work to move along it.
Which brings us to our final section, part 5, the system's total energy.
It's time to scale up from the micro to the macro level to see how these rules let us build up the energy of a whole universe of charges. Thankfully, the math for complex systems is incredibly forgiving, and that's all thanks to the superposition principle. Because potential is basically just work, and work is a simple scalar number, you don't need to do any crazy, complex vector geometry to find the total potential of a messy system. You literally just calculate the individual potential of every single charge at a specific point and simply add those numbers up. It's just basic addition.
Let's narrate how this builds practically, step by step. Imagine a completely empty universe. Step 1. We bring our very first charge, Q1, from infinity to its spot. Because there are 0 other charges around to push against, this takes absolutely 0 work. Q1 gets a totally free ride. But the moment Q1 is placed, it creates an invisible landscape, a potential field spreading all around it. Step 2. Now we bring in a second charge, Q2. This one definitely doesn't get a free ride. We have to actively do work against the invisible landscape established by Q1 to force Q2 into its final position.
And that brings us to the grand finale. The total potential energy of any system of charges simply equals the total work done by an outside agency to assemble that whole setup from infinity. All that physical work we just did pushing those charges together, it didn't disappear. It gets permanently locked in, stored as the electrostatic potential energy of the entire system. It is exactly like coiling a giant invisible spring. Well, we've covered a lot of ground today, mapping these unseen forces that essentially hold our physical world together. But before we go, I want to leave you with a bit of a mind-bending puzzle. We established that moving along an equipotential surface requires absolutely 0 work. Now, inside a perfectly conducting metal wire, charge can move freely with practically 0 resistance. So, does that mean the entire inside of a conductor is just one giant equipotential volume? And if it is, how does electricity actually flow to power the screen you are watching this on right now? Think about that for a bit, and we'll dive into the fascinating world of everyday electronics in a future explainer. Until then, keep questioning the invisible world around you.